Hi there, everyone. I'm Nick Sharp, and this is a talk about Geometry Central, which is a data structures and algorithms library for geometry processing in C++. This talk is also by Keenan and is presented as part of the SGP Graduate School Geometric Computing Sessions in 2020. So the general scope of Geometry Central is that it's a C++ library of data structures and algorithms. So this is not like a GUI program that you would open up and use your mouse to accomplish some task. It's a set of low-level tools that you would use to implement your own algorithms or applications. And right now, Geometry Central is mainly focused on surface meshes, at least for the time being, though we do have some useful utilities for other parts of geometry processing. What inspired us to make Geometry Central is that we found that often we encountered algorithms in geometry processing which were really easy to describe. Oh, you take this mesh, you split these edges, you compute this data, and then you find a direction field, or you parameterize it, or so on and so forth. And these would take just a few minutes to describe on the whiteboard, but maybe days of code writing, often because you had to go back to the very lowest level basics in order to implement these algorithms. So our goal with Geometry Central is to leverage abstractions to make simple tasks simple. So this is in contrast to, for instance, being the lowest common denominator. That's not a goal of this library. The goal of this library is to have a really useful, powerful, and sort of feature-complete set of classes and abstractions that make it easy to implement whatever crazy idea you might have. And we think that in this way it's a nice complementary approach to the geometric computing ecosystem as it currently stands. A little bit of more logistical information, so more details about Geometry Central are available online. And Geometry Central actually doesn't even have a GUI, because it's really focused on just these data structures. However, we have a separate project called Polyscope, which is a general purpose viewer in C++ and Python, which fits really nicely with Geometry Central, and you can also check out separately at polyscope.run. You can even use Polyscope separately for other projects and other geometry processing libraries if you're so inclined. But back to Geometry Central. So the most important and sort of most fundamental class in Geometry Central is the surface mesh data structure. And our goal here is really to create a general purpose surface mesh that supports all the kinds of operations you might want to do, from mutations to iterations to higher level algorithms and so on and so forth. And it's important that this surface mesh not have restrictions with respect to faces, so it can't be just a triangle mesh or something like that. It doesn't require manifoldness and so on and so forth. This is important because when you restrict your core data structures to a limited set of inputs, as soon as your user needs to leave that limited set of inputs, all of a sudden the whole library sort of stops being useful. So it's really important to handle the most general case possible, which is what we do with the surface mesh. This class supports things like iterating through the elements in a mesh, things like navigating through adjacent elements, so like for each face adjacent to a given vertex. It lets you do things like modify a mesh by splitting edges, and we also help you to store data associated with a mesh via a system of containers that can be indexed with elements. And of course, as we're doing all of this, we want to keep it efficient. So we find ways to implement these operations that lead to nice, sort of friendly-looking user-facing code, but use very efficient computing methodologies under the surface. So how to represent surface meshes is sort of a very fundamental and sometimes divisive question within geometric computing. One of the most basic things you might do is just use a face vertex listing. So this would be like a rectangular array where for every face you store the indices of all the vertices incident on that face. And the nice thing about this is that it's really simple and easy to implement, but some downsides are that it can be expensive to update if you need to, say, delete a face. And even worse, what inevitably seems to happen, at least in my experience, is that partway through some algorithm, you discover you need to iterate over some other adjacency relationship, like, for instance, all the faces incident on some vertex, or the faces that touch some edge, and so on and so forth. So you end up building up arrays that cache this data, and before you know it, you have this whole slew of arrays that you're now stuck managing manually as a user, rather than just having them as a part of the data structure. So there are lots of libraries and techniques out there that do cool things with face vertex lists, but we take the opposite approach of Geometry Central and use a rich reference-based connectivity structure. So these go by names like half-edge meshes, directed edge meshes, winged edge meshes, and so on and so forth. So these are a little bit more complicated. You'll define some set of relationships, like each face has a pointer to the half-edges instant on it, and each half-edge knows which edge it touches, and so on and so forth. But the important thing is you're storing a fixed constant set of reference relationships, and these allow you to easily update pretty much anything you'd want to update in constant time. And more importantly, they sort of encode all possible adjacency relationships. So you never have to run around and pre-compute some array of vertex neighbors or something like that. You can access all this kind of data by just traversing your mesh data structure in the right way. And I think that these have sort of gotten an unnecessarily bad reputation in some parts of the geometric computing community. And one reason why is that sometimes they get implemented in silly ways, and in particular in ways that aren't friendly to the user or to the programmer. In particular, you should not implement these kinds of data structures with raw pointers. You should use indices, because manipulating pointers in C++ has so many pitfalls to fall into. You want to avoid those. Just use indices. Another mistake you could make would be to dynamically allocate your elements. If you're calling new to create each new vertex object, these things end up scattered in memory, and you pay a huge performance overhead. Instead, you can just logically store your mesh elements in flat buffers. And the most high-level, most important thing of all is that none of these details should be exposed to your user. In particular, the user shouldn't care whether you're using a half-edge mesh or a winged edge mesh or whatnot, and it shouldn't matter to them whether you're using pointers or indices under the hood, because all of these things should be abstracted away when the user actually interacts with them. And with all of these properties, reference-based meshes actually become really awesome, because everything is efficient and constant time and so on and so forth. But now your data structure is super powerful and can do pretty much anything you want it to do. So this is the philosophy we've taken with the surface mesh in Geometry Central, and I think it ends up being really effective to work with. So to give you a little bit more details under the hood about how the surface mesh in Geometry Central works, well, as I mentioned before, all of the connectivity is encoded using dense buffers, which are quite literally just standard vectors of indices. In particular, we use a half-edge mesh style representation, but as a user, this shouldn't matter to you at all. You shouldn't care that we're using a half-edge mesh. So all of the connectivity in the half-edge mesh ends up being stored in these dense arrays, just dense arrays of indices, so no dynamic allocation, no pointers, and so on and so forth. And if you do something like adding an element to your mesh by, say, splitting an edge and creating a new vertex, then we lazily expand these buffers of arrays in order to create space. So then this means that all of these operations end up being an amortized constant time and rarely incur memory allocations, which helps make the code really fast. And similarly, if you go to delete an element, we don't immediately delete the element from the mesh. We just logically mark it as deleted and then continue processing. And this again makes deletion operations extremely fast and efficient. And of course, none of these are details you have to care about when you're interacting with the mesh class. It's how we do things under the hood to keep them efficient for whatever application you might be designing or whatever algorithm you might be implementing. A few more little details. We play some clever tricks with manifold meshes, which allow you to actually represent less connectivity by doing some implicit arithmetic on indices. So this is just an efficiency optimization. And we also extend the traditional notion of half-edge meshes to support non-manifold meshes by storing a few extra similar buffers of data. So when you're actually interacting with this half-edge mesh, usually you work with You work with one of the elements. So for instance, the edges in the mesh. And in my opinion, it's really, really important that your element, an edge in a mesh, or a vertex in a mesh, or a face in the mesh is not an index to you as a programmer. It's not an unsigned int. Because the downside is that if your elements are unsigned ints, in terms of the language, you've lost all semantics about what it means and what it does and where it's safe to use. So our mesh elements are not much more than an unsigned integer. It's just an unsigned integer that also knows what mesh it goes with. But wrapping this in a meaningful type allows us to do all sorts of useful things, like if you're supposed to give us a vertex and you give us an edge, then you can throw a compiler error. You can also augment these with useful operations like edge.neighbors and so on and so forth. And of course, these types support all the useful operations you might suggest, like hashing them, sorting them, printing them, and so on and so forth. Once you have one of these elements, we also have a system of containers, these mesh data containers, like for instance an edge data, which you can use to store any values you might have associated with the mesh. So here I create an edge data object, which is initially filled with zeros. And then for any edge in my mesh, I can index that edge data and store some value in it. So these can be indexable, But the really, really cool thing is that these containers are aware of the mesh that they go with, so they can automatically resize. So for instance, as you're deleting and adding elements to your mesh, these containers are smart and they dynamically, efficiently resize themselves so that it's always valid to index them with an element of your mesh. Together, these properties remove a whole bunch of the sort of boilerplate error-prone code you might often have to write to keep track of data as you're modifying a mesh. And of course, under the hood, these containers are still backed by an eigenvector, which is a very common vector type in geometry processing. So if you need to, you can just access this raw underlying type and do linear algebra with it or whatever else you might want to do, pass it to some other library, and so on and so forth. So as I've mentioned a few times, we really believe that the user should never touch this underlying mesh data structure. And to support that, we've implemented all kinds of adjacency and iteration operations you might want. So this list is pretty extensive, but you can do things like for a mesh, iterate over all its vertices, its edges, its corners, and so on and so forth. For a vertex, iterate around the adjacent edges or the adjacent corners. For a face, iterate over all the adjacent half edges or faces, and so on and so forth. And similarly, we offer tons of routines for mutating meshes, for doing high-level operations on meshes. So you should never have to actually work with these lower-level buffers of arrays. And we think that these are really important because this is what makes it easy for you to sort of in natural language write out whatever kind of algorithm you might be imagining on your mesh and then have it be really fast because there's this careful implementation under the hood. So to give a more sort of in-depth example, let's hop into some live coding and use this paradigm to implement 4-to-1 subdivision. Now, of course, you could also just call built-in routine to do 4-to-1 subdivision on a mesh, but I think it's a nice example to look at what this mesh data structure gives you and what code in Geometry Central looks like. So we're going to hop into a terminal here, and I've got a simple little class here, which just takes some of the boilerplate. So here we have some includes, so we're including the Geometry Central mesh classes, and we're going to be flipping edges, so we want a manifold surface mesh, and as well as some mesh loaders, and of course all the Geometry Central types live in respective namespaces, so we're going to bring those namespaces into scope, and also include polyscope, which allows us to visualize our surface meshes. This is just a standard argument parser, and then down here we load a mesh from file. You'll notice that here we use unique pointers to store the mesh, and this is an alternative to just using raw pointers in C++. And I highly, highly recommend that you make use of unique pointers in your code. We have a few little blurbs about them on the Geometry Central doc, because they avoid a lot of the most, prevent a lot of the most irritating pitfalls you can fall into with pointers in C++, like deleting it twice or forgetting to delete a pointer, and so on and so forth. So this code just loads the mesh from file. This set of args gives us a file name like spot.obj, and our surface mesh parser supports all the formats you'd probably expect. And then down here we register this mesh with polyscope to do visualization. So we initialize the visualization engine. We register the surface mesh by passing its vertex positions from the geometry and its connectivity represented as a face vertex list. And finally we show the mesh in a UI. So if I go compile this real quick and run it, and let's grab a mesh file. Spot the cow is always ready for action. Sure enough, here we load up the mesh and we can see it. It has edges and faces. This one happens to be a triangle mesh, although the code exactly as written before would have worked on a quad mesh or any more general polygon mesh. And we can click around, inspect the faces, inspect the vertices, and so on and so forth. So let's see what it looks like now that we have the basic mesh loaded up to implement 4-to-1 subdivision. So as you might know, 4-to-1 subdivision can be implemented by first splitting every edge, split all edges in the mesh, and then for each edge which is incident on for each new edge which connects an old vertex to a new vertex, you flip it. So flip edges, connect old vertices to new vertices. And this is a nice example for the mesh data structure because it requires us to traverse the mesh, it requires us to work with some different vertex handles, and it requires us to do some basic mutation operations. So to split edges, quite simply, we're going to say for edge e in mesh edges, and this loop then is going to iterate through all the edges of the mesh. oops, got my bracket pointing the wrong way there. There we go, for each edge in the mesh. We're going to first get references to the two endpoints on either side. So vertex 1 is going to be edge.tail vertex. So this is the vertex on one end of the edge. And then we also get the vertex on the other end of the edge. And we're also going to need the positions of those two vertices, because when we split the edge, we need to position the new vertex somehow. So let's access the geometry. And I'm going to talk in a minute about what this geometry object is. But for now, we just care that it holds vertex positions. And the position of the other vertex. So then now we just want to split this edge, so we can call vertex new v equals mesh split edge triangular of our edge E, and we want the vertex that results from that edge split. And now we need to position that new vertex in space, because right now it's just a logical vertex. It has no position in space. So we're going to compute a new position as the midpoint of the two old positions. And then we're going to assign that new position as the position of the new vertex. Now, if we ran this code as written, well, every time we do an edge split, that creates a few more edges. And then this loop would keep going and try to split those edges, which would create more edges, and it would try to split those, and so on and so forth. So we want to make sure that doesn't happen. So we're going to create an array, a Boolean valued container, which for each edge in the mesh tells us whether or not it's new. Let's call it orig edges. So that's going to be defined on our mesh. And initially, all of the edges are original. So it's this true will populate it with all trues originally. And now all we're going to do is iterate around the new edges that are incident on this vertex. And for each one, mark it as not being an original edge, because we just created it by splitting. So that makes sure that this loop doesn't keep running and running and running and running. So I think this looks good here. So let's go ahead and compile that and see if I made any syntax errors. Let's see, mesh.split edge. Can I not spell? Split edge triangular of E mesh.split edge triangular. Ah, here we go. I didn't load a manifold surface mesh. I loaded a general surface mesh. And it's not so easy to split edges on a general surface mesh. So let's make sure we load a manifold surface mesh. You actually can still split edges on a non-manifold surface mesh. It just looks slightly different. And now that I've promised that my mesh is going to be manifold, we can split these triangular edges. And in our other window here, I'm just looking at our original mesh because I didn't visualize it. So let's go down to Polyscope here, and we don't just want to visualize the original mesh, so we'll come up here, and before we do any edge splits, we're going to register the original mesh to visualize it with Polyscope. But then after doing these edge splits, we're going to visualize the subdivided mesh. Sub mesh, and do it again. So that's going to register a second mesh with Polyscope for visualization after we've done these edge splits. So if we run this, we see in our second window here that, sure enough, right now it's showing both meshes, which are on top of each other. So there's our original mesh. And after doing these edge splits, sure enough, we've split a whole bunch of edges and created a whole bunch of new vertices. So this is looking good so far. Now let's implement the second half of subdivision, of 4-to-1 subdivision, where we flip any edge, which connects an old vertex to a new vertex. And the easiest way to do that will actually just be to build up a vector of such edges that we want to split. So let's go standard vector edge, that we want to flip. And we're also going to need to keep track of which vertices are these original vertices. So we'll have a second container defined on vertices, which hold booleans, and initially they're all original. As we split each edge, we're going to need to mark it as not being original. And now we're just going to say here, so as we're looping around the edges instant on our new vertex, let's get the other endpoint of that edge. So vertex other v equals e dot other vertex of new v. So this is saying find the other vertex instant on the edge that's not the new vertex. And then, and I actually created a duplicate variable here. So you'll notice I have an edge e up here and edge e up here. C++ is fine with that, but it's a little confusing, so let's not do that and call it en, eneighbor, instead of just e. And we'll say if the opposite vertex is not an original vertex, and this other vertex is not VA and it's not VB, then this is an edge we're going to want to flip. So to flip, let's add this to our list of edges to flip. And then finally, we're going to come down here and say for edge E in edges to flip, we're just going to call mesh flip E. And that's it. So that'll flip all the edges connected from old to new vertices. Let's see if there are any syntax errors. And sure enough, it compiled just fine. So let's see what this does in our other window. Once again, these guys are on top of each other, so it's drawing both at once. There's our mesh we started out with. And uh-oh, something went wrong. Let's see what happened here. I'm going to guess that we flipped the wrong edges. So let's take a look at this and see if we can spot the bug. We only want to do this if the other vert is an original vertex, not if it's not an original vertex. Recompile. And there we go. I like that a lot better. So this is a 4x subdivided version of the mesh we started with. Great. So as I mentioned before, this is sort of a low-level routine, and really you'd probably just want to call a 4-to-1 subdivide function to do this for you in practice, but I think it gives a decent example of some of the data structures that Geometry Central offers. Sweet. So let's hop back into our slides here and talk a little bit more about the design of the library, and in particular this geometry class and what's going on with it. So in addition to the connectivity of a mesh, the next most important thing is its geometry. But you'll notice that very much by design, we separate these two notions in Geometry Central. And there's a couple reasons to do that, but most importantly, they're just logically separate, right? There are many ways to define the geometry of the surface, and there are many ways to define the connectivity of a surface, and you should really be able to mix and match those together. You also might have multiple notions of geometry associated with one set of mesh connectivity. Our other observation is that there are lots of different ways to define quantities and to define data that might give you the geometry of a surface. And I think this is actually something we see a lot of at SGP, so there's a lot of awesome papers where somebody might come up with a new representation for, say, the hyperbolic geometry of a surface, or a little bit more concretely, a new discretization of Gaussian curvature on a surface. And now what you want to do is you want to take this new notion of geometry and use it to run higher level algorithms. And in other libraries, you might basically be stuck doing this from scratch because you've changed one of your low-level definitions. But we wanted to set up our geometry in a way that makes it easy to immediately continue running higher-level algorithms, adopting these new basic notions. And the way we do this is that we use polymorphic geometry interfaces which fill buffers with various quantities. And I think this will be clear when we look at an example. But the benefit of this is that the exact same sort of application code can run out of the box on lots of different notions of geometry and how it's discretized. And one important design decision here is that you could also implement a similar thing using C++ templates, and there are some libraries that do absolutely amazing things with C++ templates. But a downside to this is that templates can be a little bit difficult to work with from a user perspective. So we intentionally wanted to avoid sort of template incantations to make this more friendly to novice programmers and whatnot. So let's look more concretely at what these geometry classes look like. So suppose you want to represent geometry via vertex positions. Well, you just need to define the data as a 3-vector per vertex in your mesh. And then you could create a vertex position geometry object, which depends on your mesh and the set of vertex positions. However, a different way to define the geometry of a mesh is via its edge lengths. So here again, if you have a length associated with each edge, you could create an edge length geometry object by passing in a mesh and a length for each edge. Now with either of these strategies, or many other strategies you might use to define geometry, you can just call geometry.require Gaussian curvatures, and this object will populate a buffer of Gaussian curvatures at each vertex, which you can then access with any vertex. And the important thing about this design is that now suppose you have some new clever way of representing Gaussian curvature, well, you can just override that one function in the class and create a new geometry object that uses your new definition of Gaussian curvature, and then even continues to use that new Gaussian curvature to compute other quantities. This has some other benefits in that it reduces boilerplate data management code, so you may find that your geometry code is full of passing around these simple buffers of basic quantities, and this way they're all sort of gathered together and managed by the geometry object. And we can also do things like support mutation. So suppose you reposition the vertices of your mesh. Well, just calling geometry.refresh quantities will automatically invoke all of the necessary methods to repopulate your buffers. So this is sort of a great quality of life thing, which both makes your application code simple, but kind of more importantly allows it to easily make use of more generalized notions of geometry. And when you're using this as in an application, well, your algorithm just needs to specify what data it needs. So we implement a bunch of subroutines which accept different geometry via interfaces. So for instance, if your algorithm requires the intrinsic geometry interface, that means you need to pass some geometry interface, which has things like edge lengths, face areas, corner angles, and so on, which are, as we know, all the quantities in intrinsic geometry. So for instance, you can specify one way to specify that is with edge lengths. Then there's extrinsic geometry, which adds in addition quantities like dihedral angles and mean curvatures, or even all the way to an embedded geometry, which has notions like the position of a vertex or the normal of a face, and so on and so forth. So these allow you to sort of, when you're writing an algorithm, specify just the quantities that you actually need. And I'd be remiss if I didn't mention a few other niceties that we have in Geometry Central. So one of these is rich mesh classes. Rich mesh IO that allows you to take these vertex data, etc. containers and automatically write them to file, and also can directly serialize our mesh representation for faster loading and even loading of meshes that can't be represented as a face vertex adjacency list. We also have things like surface points that give a whole bunch of utilities for computing with arbitrary locations on surfaces. For instance, a point that might be in some face or on some edge or at some vertex, and so on and so forth. And then we also have a whole bunch of linear algebra routines for all the standard things you might expect, like interfaces to various linear solvers, some higher level optimization schemes, and so on and so forth. And one thing I'm not going through here is all the other various higher level algorithms we have in Geometry Central. So this includes things like direction fields, geodesic distance computation, some parameterization routines, all the kind of things you'd expect to do in surface geometry. And we're constantly adding to this list. So starting to wrap up here, Geometry Central is a very actively growing library. We're constantly adding new things to it and taking feedback from people who are using it and looking for ways to improve it. Some things that are on the horizon are using the same paradigm that our surface mesh uses to implement volumetric meshes and point clouds and so on and so forth. And also just growing our library of classical algorithms. So I really encourage you to go check out Geometry Central. So we have tons and tons of documentation. There's tutorials. We worked pretty hard on the build system, so it's easy to build on various platforms and things like that. And our GitHub page is pretty active, so we really encourage you to participate, request some feature you might want, any bugs you find, or contribute whatever cool algorithm you've come up with. And one last reminder that the visualizations in this page used in the tutorial were done via Polyscope, which you can also check out at polyscope.run. So I think that's all I have for today. So please enjoy everything as that's a part of the SGP's tracks and sessions this year. And don't hesitate to contact myself or Keenan or anyone else involved with Geometry Central if you have any questions.